Okay, ladies and gentlemen, good morning. This is Resh Mahaber. Let's double check, make sure we're recording. Beautiful job. Okay. This is Resh Mahaber signing on again from Wayne State University. I want to talk about my Math 1800, which is pre-calculus series and today we're going to discuss logarithmic functions, okay, because we just got done talking about all the other functions in the world and how to graph them and how to work with them, and we had just got done talking about exponentials. But exponentials has a double story, okay, because when you look at the light, you got to look at the dark. The dark side of exponentials are the guys that undoes exponentials, which is logarithms. And exponentials, we really didn't do a gigantic lecture about it because we need to know about logarithms to really talk about exponentials a great deal. Okay, so here we go. Let's start. This is section, I think it is 4.2-ish. 4.3-ish. I think it's 4.3-ish. 3. Okay. And this is talking about logarithmic functions. I see I still cannot spell today, but that's okay. We're going to get through it. All right, logarithmic functions. No big deal. I guarantee you this is probably going to be the easiest section. Now, if you remember, because it just requires old knowledge. When I mean old knowledge, I mean it just requires your laws of exponents, okay? So if you remember our last example we left off with, I asked you to graph an exponential, and I said, don't worry about finding the x and y intercepts. We're going to have to use some magic later. Okay, well, this is the magic I was talking about. So let's recall the last example just to make sure you guys didn't get a brain disease from then and now. And I don't remember exactly what it was, but I know what it was like. And it was one of these guys. F of x equals minus, and I'm going to use a base you guys aren't familiar with, but you will be familiar with soon, and this is e. Okay, negative x plus 3 minus 4. And guys, do not freak out about this. E is no big deal. If you want to know what e really is, e is like pi. No, pi is like 3.141592653589793238446 and some stuff that I can't remember now. Well, e, I'm not that good with e. I don't use e in explanation. You normally keep it in this kind of form. It's 2.71, but it has a very special name, okay? E is called the natural number. Now, why is it called the natural number? Because some 150 years ago, we started to understand that the natural number occurs in everything that's natural. What do we mean by natural? It's nature, right? So if you ever guys get the opportunity to take a class called complex analysis, you'll realize that E is really the function that predetermines things like genetic sequencing and being able to predict where peptides and proteins and amino acids are actually going to be at on like a DNA or RNA strand. So E is a very, very important number when we start talking about computer modeling of DNA and actually extracting genetic forms. Like that's how they're doing cancer research right now. They're trying to figure out what are the defective or overproducing cells or overproducing parts of the genetic sequencing and extracting that piece of the DNA or taking out some of it so it's not going to be passed on to a kid. It's kind of like Gattaca, the movie, if you've ever seen it. All right, and I would encourage you to see it if you'd like. You'll get kind of what I'm talking about. Okay, so that's what E is, and it goes on forever. It doesn't stop. All right, but this is no different. We've talked about, remember, when we graph this, and this is what the idea is. I want to graph this. Okay, I'm going to go through it very, very quickly. When we graph this, once again, it's one basic. Here's the basic graph. And I talked about that any exponential is going to look like this. A to the x is going to look like this with an a horizontal asymptote. See how filthy that graph is? It's ugly. So let's make my A E. Okay? So now 2. That's my basic graph. 2. And this is obviously 0, 1. Now, some instructors I know would yell at me for graphing like this. Now, what's the order? Left, right, flip. Okay? So I'm going to go left 3. Remember, this guy is counterintuitive. Right? So this is f of x equals e to the x plus 3. So we're going to go, remember, if you move an asymptote left, it ain't going anywhere. It just doesn't make sense to go anywhere, right? But this guy, which is right here, bingo. Okay? That's 1. 2. All right? So now we need flips. Now in this one, we have both flips. Let's discern between the two. This guy is your left-right flip. This guy is your up-down flip. Okay, so what this means is we have a left-right flip and we have an up-down flip. Okay, so here we go. Let's left-right and up-down it. So we're going to start with our previous graph. I'm going to go left, right first. Okay, the asymptote will not move. 1, 2, 3, 1, 2, 3. So the point that was right here should flip over to this side. They see how it's going upwards. Now it's going to start going downwards. Okay, so this is your left-right flip. And then finally, I'm going to take this graph and now do a up-down flip. And again, the order does not matter which way you do your flips. So go ahead and do your flips backwards, meaning upward and down, then left and right if it makes you feel more comfortable. 1, 2, 3. Don't do that. That's here. I still have a horizontal asymptote. And booyah and booyah. Pretty simple so far, right? And then finally for, I think I still have something else. What do I have to do? Oh, yeah. Don't forget that. Then we still have to do a drop down 4. Actually, let me make this one left 3. We'll do that just to make sure everything's all pretty. All right. So now we need to drop this thing down 4. All right. So boom, boom. Let me get some black out here. Go down 4. Okay. So let's rock with our video. Boom, boom, boom. Now, be careful. If we drop down, don't forget the asymptote is part of the graph. So I'm going to drop the horizontal asymptote down 4 units. 1, 2, 3, 4. Done. All right. Now this guy that's at 3, 1, that should also drop down 4. -1 should drop down 4. And as a matter of fact, it should be 1 away from the asymptote. Don't be drawing it all on top of the asymptote. Beautiful. All right. Now this is where we left off. Okay. Now, remember, this section is about logarithmic graphs, not exponential graphs. So why the heck it's an exponential graph doing next to a logarithmic function section? Well, because we need logarithmic functions to do certain things. And what are those two things? We need them in order to find x-intercepts. Well, actually, the y-intercepts, I think you guys can already do, as a matter of fact. And if you notice in class, I'll say just do the y-intercept. There's your y-intercept. And if your function is f of x equals, what was this guy? Negative e to the negative x plus 3 minus, or plus 4. Let's say minus 4. What was it? Minus 4 plus 4. Plus 3 minus 4. Okay? Then it's pretty simple. Make the x 0. Do not freak out about e again. It's just an irrational number. So if you make f of x equal, plug in 0 for x, this becomes negative e to the third minus 4. Now you're probably saying, what is that? Well, e is about 2.71. If you want to estimate it, let's just call it 3. So this is like saying 3 cubed, which is like negative 27 minus 4, which is negative 31. This is like negative 31-ish. Pretty easy, isn't it? So this is like 0, but don't you dare write negative 31 there. That is not what it is. This is what it is. Here's the problem, and you guys are probably saying, well, this graph has no x-intercept because of the asymptote. Yes, you're right, but how would you prove that to yourself? The x-intercept is the pain in the neck. So I'm going to show you what we run into when we try to find the x-intercept. I'm going to take the same function, I'm going to set it equal to 0, and then we're going to start solving. Okay, so when we start solving, we get 4 equals negative e to the negative x plus 3. I added the 4 over. I'll multiply by a negative, and we get here. Now, this is what leads us to section 3.3. This right here. And why? Because the question now comes down to is, I'm going to make a little cloud for you, a little think bubble. How in the world do we solve for x? That's the question. How do we solve for x? Well, the answer to this is logarithms. Hence why we need to talk about logarithms. Okay, because logarithms, and this is the big story. You guys remember the order of operations? I'm going to show you where logarithms come into play. Okay, so here's the order of operations. This is Rush being lazy. Okay, it's parentheses, exponents, multiplication, and then addition. And some of you guys are probably saying, please excuse my dear Aunt Sally. I don't have any aunts named Sally. Okay, so I don't know any reasons to excuse them. Acronyms have no purpose once bigger meaning is found. So find bigger meaning, and then you will no longer need acronym about an aunt named Sally. Unless you really do have an aunt named Sally that needs excusing, then I understand. Okay, so here we go. Addition has an inverse. Okay, one inverse. That is subtraction. I'll write all the inverses in red because they're figments of your imagination. Multiplication is division. Okay, now notice these two have one inverse. Exponents, though, he's an interesting character because depending on what's missing, we have a different inverse. And this is why, okay? So exponents have this thing called roots. Now, what are roots for? Well, let's talk about this. If you have 2 to the third, we call that exponents. All right, so if 2 to the third, the unknown thing is the answer. This is what we use exponents for. If we look at roots, though, roots, we only use that when something is missing. What's the something that's missing? And that's the base. Right? So we would cube root both sides to solve this, right? But we never talked about how do we solve an exponential. So what if an exponential, and once again, we're talking about an exponent looking thing because it's 2 to the x equals 8. How do we break into here? How do we break into there? We can't use roots because what are we going to do? X rooted? That doesn't help me solve for x. That's ridiculous, okay? Bottom line is we've got to find some way to undo that base. And the only thing that we have is not this. I don't know what that's doing there. Is logarithms. So here's the point, guys. Exponents has 2 guys that are inverses. It has 2. Logarithms and exponents. Now you're probably saying to yourself, well, why is exponents the weirdo that has 2 inverses? Because it's this gigantic property that no one really emphasized on during grade school. So let me emphasize on it now. Addition has 1 inverse because of this property. 3 plus 2 equals 2 plus 3. Multiplication has 1 inverse because of this property. 3 times 2 is 2 times 3. Is it ringing a bell for anybody? Anybody know what this thing is called? Exponents is 2 to the third power the same as 3 to the second power? Obviously, absolutely not. So what this means is, depending on what is missing, whether it is this, the exponent's missing, meaning it's an exponential. This, the base is missing, meaning that this is what we call a polynomial. And this, which is just arithmetic, okay, depending on what's missing, you're going to need one of 2 inverses because exponents, and here's the word that they didn't emphasize on, exponents are not commutative. 2 to the third is not 3 squared, so it needs 2 different inverses depending on what is missing. That's what it comes down to. Okay, multiplication, you can always use division, no matter what. It's commutative, so no matter which way you write it, you can still divide it out. Same thing with addition, you can still use subtraction. But if exponents, if that base is missing, you better use a root. And if you have an exponential to solve for that, you're going to need a logarithm. Man, isn't that crazy? I gave you guys a 13-minute intro of why we need logarithms. We need them in order to graph exponentials. We need them basically strictly for exponentials. So we need a brand new topic called logarithms. And this is a topic you've seen before, so I'm going to go over it about a couple different things, and I'll give you some cool little properties about it, which will take us into 4.4. Okay, so let's talk about logarithms for a second. We're going to segue from here, and then we'll go back to exponentials to finally find that x-intercept. Okay, so here's 4.3, legitimately. Log functions. Now, I know the first part really wasn't legitimately that. I kind of start off like that. Okay, so what you got to get is this. When we talk about exponentials, we have a base, we have an exponent, and we have an answer. And yes, you learned all these laws of logarithm of exponent properties, right? Now if you got the same base and you're multiplying, you add the exponents. If you got the same base, right, and you have an exponent raised to an exponent, then you multiply the two. Right? You got the same base, and you have 2 exponents, and they're divided by each other. You subtract the exponents, right? You got all this stuff from basic algebra, right? Which I hope all you guys have mastered by now, okay? Because you're going to need it for this. So if you have this, remember the goal behind an exponential, right? And note, we're in a logarithmic section. I'm talking about an exponential, is to solve for this. We need to solve for the exponent. So the question is how do we get the exponent by itself? Answer is this. We need to introduce a new function. So we introduce a conversion, and this is just a conversion, no big deal, okay, of a logarithm. So when we say log, we have to designate a base. Guess what? The base is the exact same as this base. So log is an operation. The same way we write this as a superscript, right? Log is an operation. The base will be designated as a subscript. And remember, we don't know, and I want you to keep in mind the example we just had, 2 to the x equals 8. So we know what the base is. We know what the answer is. We just don't know what the exponent is. So the answer is actually written right here. By the way, they don't call it the answer. I'm just calling it that so it looks pretty. But it's actually called the argument. Okay, so I try not to church things up with fancy languaging. But if you read a book and you hear it, it's actually called the argument. Okay, so and finally, what is it equal to? What's the only piece of the puzzle we didn't use? It's equal to the exponent. Okay, so here's my point. If we use this problem and we converted it over here right into a logarithm, the operation that we would use is log. The base, well, what base did they use? 2. What was the answer? 8. And then what is it equal to? Well, that would be, if we just convert it directly, it would be equal to x. Okay, now you do need to know, so if you have to solve this, you should probably be using common sense at this point. Okay, what I mean by common sense at this point, you should be able to tell me that the answer to this problem is 3. Why? This is the reasoning. Notice the conversion. I got 2 arrows here. You sometimes will need to have to go back to exponential form to think about these. And that's why I said they're closely related. You need both. And actually, oftentimes, people get confused on which one to use because they're so closely related. Okay, so this is where you need to start focusing in on the differences. 2 to the third power is 8. Okay, so this is a very easy problem to understand that this is actually equal to 3. Okay, so that would be the answer to this. So what is the real purpose behind logarithms? Let's talk about purpose behind logarithms. Well, it's kind of like roots. What's square root of 2 really? Don't write this down. I just want you to look at it. Is there another expression or way to represent that? No, it's irrational. It's like 1.4 and some change, okay? It's irrational. So we don't write 1.4, but we just know what 2 whole numbers it's in between, which helps us predict which value it is, right? Well, it's the same purpose if I were to say solve 2 to the x equals 7. You would convert this. It'll be log, the base is 2, the answer is 7. It's equal to the exponent, which is x. So we're saying that the exponent has to be this blob. Now, is there some beautiful little number like 3 was with this guy? Absolutely not. 2 to what exponent is 7? We don't know. But I know something that because I know my laws of exponents, 2 to the third power is 8. This is what's happening in my brain, by the way. And 2 to the second power is 4. I could tell you that x has to be in between 2 and 3. So this means that log base 2 of 7 is 2 point something. Do I know what the something is right now? No, and as a matter of fact, you won't know what the something is until you get to Calc 2, okay? But the point is you should be able to tell me what 2 whole numbers is in between for graphing purposes and for solving purposes. Make pretty good sense, right? All right, so that's the purpose of logarithms. So now if you're still uncomfortable, what it comes down to is we just need to do a ton of examples. And I try to keep these videos about 20 minutes long, but this one's going to be about 20, 25, because I feel like we need a little bit of practice. So here we go. I want you to evaluate these logs. Okay, this would be a good time once I put the logs on the board or on the paper here, to take some time. So this is A, this is B, log base 3 of 9. Take some time and just pause the video. Try to solve these yourself. And then once you do that, then come back and look and see if you got the right answer. What did I do again? I have these big hands and they tend to touch everything on the screen. Okay. How about this one? Log base 10 of 1 over 100. That's a good one. Do I have anything else that's good for you guys? Oh, what the heck? How about something that's uglier? Log base, and I'm going to change the instructions on this one. I want you to estimate, meaning finding 2 numbers that's in between. Log base 3 of 10. I feel like I'm giving you a lot of 10 stuff. Yeah, right. Okay, that's fine for right now. And we'll do more. All right, guys, pause the video. And what the heck? Log base, let's not Let's get rid of this estimate one. Log base, I want to do one more exact guy. Log base 10 of 1. Let's do log base 10. Let's not do 10. Let's do 2 of 1. You know why I keep doing log base 10? Because that's when a log is not, if it just says log of 2, it's assumed to be 10. It's assumed to be 10. So I'm putting base 10 here, but eventually I'll start getting rid of it. All right, guys, pause the video and take a second and try. And then when you click on, we'll talk about it. All right, go. All right, welcome back. Here we go. So what do we need to do? Let's switch colors so we get emphatic about this. Is what you need, all you need is this. You'll notice I'll always come back to this. Is that if you know how to convert this, this is good. Okay, so let's just take a look-see here. This is equal to something I don't know. Why? What is the conversion? You turn this back into an exponent to think about it, right? And some people will get good that they could only have to turn it back and they can just say 2 to what power is 8. But if you can't, then you're going to say the base is really the base of this exponent. The exponent is really the answer, which is the box in this case. And the answer is really what this is equal to. So the answer of the logarithm, which is 8, has to be equal to this guy. Now use some common sense. 2 to what power is 8? And actually, these are the easiest ones to solve because you start multiplying 2's until you smack on 8. So what is that? 2 times 2 times 2. That's 3/8. So the answer's got to be 3, so this is 3. Very simple. Okay? Very, very simple. How about this one? Then I'm going to start saying it without writing it. 3 to what power is 9? Obviously 2. Here is the justification. 3 to the second power is 9. Done and done. How about this one? 10 to what power is 100? Obviously 2 again. Why? Because 10 squared is 100. It's pretty easy, right? Now here's where it gets fun. 10 to what power is 1 over 100? Now is this one easier? Yes, if you know your laws of exponents. So 10 to what power is 1 over 100? Moral of the story is 10 to the second power would give you 100. That's what your instincts is already telling you. So what gives you 1 over? What gives you a fraction? It has to be negative. So if it was just 2, that'd give you 100. You want 1 over 100, so to flip it upside down, you want the negative 2. Done and done. Easy. Easy. Okay, how about this one? 10 to what power is 1? All right, now if you don't know this one, I should be yelling at you and you should be yelling at yourself. What goes here? 0. Bingo. All right, here we go. And I'm not even going to do the rewrite. You should know this one's 0 as well. Why? Because 2 to what power is 1? You know, this is fairly simple. You just got to take some time. And in fact, here's the point. This is your first law of logarithms. In general, log base anything of 1 is going to be what, guys? 0. Now I want you to think about this. I'm going to put this in a little fancy think bubble on the side. So this is law number 1, right? I'm going to call this law number 1. Okay? But this is not really a law. Now I want you to think about why. I want you to convert this thing back into an exponent. It should be something familiar that you've seen. If you convert it back into an exponent, the base is a, the exponent is 0, and it's equal to 1. Isn't this a law of exponents? So what this means is every law of exponents potentially can have a law of logarithms. So if you don't know your laws of exponents, everything here is unreachable. You need to go back and relearn all of your laws of exponents before you even attempt touching logarithms. Otherwise, it's going to be a disaster. Okay? It's fairly simple. Fairly simple. Okay? So, let's keep it moving. Keep it moving. So I want to go back and I want to show you why exponents undo logs undo exponentials. Okay? So this goes back to why the whole pretense of this was solving exponentials, right? Solving for that exponent, breaking into that exponent. So how is any of this relevant? Well, some guy named Euler came around. He's a I think he was a German mathematician came around. He was like, okay, well, look at this. Doesn't it make common sense? He was like, now that we know the reason why these are the answers, forget the reasons why. Yeah, I know, right? Erased everything. You can't see the reasons why anymore. Well, if you need to know why, rewind the video. And he said, let's look at the problem. log base 2, and I'm going to zoom in on this. Log base 2 of 8 is 3. We just focused on that. As a matter of fact, let's focus here for a second. And this is what Euler said. Check this out. I can rewrite 8 as 2 to the third power. So the log of base 2, when the argument or answer is also a base 2 as an exponential raised to the third power, Euler was like, the log and the exponential, he started noticing a pattern. He was like, the log and the exponential undo each other and just give you the exponent. So let's take a check. Let's do this again. Let's get rid of this. Let's blow this up. If this is really true, then I'm going to do this back in green. Log base 3 of 9, right? We're claiming that it was 2 because we did the work and we saw that it was 2, right? 3 to the second power is 2. And then Euler came around and was like, but 9 is really 3 squared. So check this out. If it was log base 3 of 3 squared, the log undoes the exponential and gives you back whatever you started with. It's really, really that simple. So Euler got to a point where he's like, oh, this makes perfect sense now. So he was like, your first thing you have to understand about the relationship between logs and exponentials is that they undo each other. They're inverses. You guys remember the concept of inverses? Yeah, right. So check this out. So he said log. If you have a base and you raise it to some exponential, you choose the exponential, but the bases have to be the same. They have to be the same, and they must be by themselves, which is a to the x. He says, based off this, that this base of a logarithm, if the argument is a to some power, is just going to leave you what, guys? Fill in the blank. That's correct. It's the power. And that's what we need. That's what we need to actually graph an exponential. But check this out. And we're not going to do this one. I'll do an easier one. To break into this x-intercept, I have to do something that gets me into this. So I'm going to give you a hint. We're going to log, but we get to choose what the base is. It's going to be e on both sides. But we have a ways to go before we get to this point. So let's just keep going till we get kind of understand. So here's the point. Logs aren't just that, what they are. They are operations. They're something you do to both sides. So I want to take this 2 to the third, so for example, 2 to the x equals 8. This might be jumping ahead a little bit, but I feel like we're okay. If I wanted to undo this, someone, instead of trying to convert it, which is still perfectly valid, you could do this, but it's a baby way of doing it. They could do what we did before, which is log the bases to the answers 8 equals x, right? And then they'll have to evaluate this, which is 3. Okay? Or, welcome to being a grown-up, logs are an operation. And so I'm going to get you to do and actually to understand is that we're going to log, but you got to choose the base. You get to choose what this is. Now, what's the most helpful base? 2. This, based off the last property, would undo each other, leaving you just the x, which is the goal. And then you just got log base 2 of 8. Notice it's the exact same as what we did before, except I feel this is more versatile because you get to choose the base. And before, all you've ever seen are things where you only needed one kind of log or you had one kind of base. Here you have many different kinds of options for what your base can be. This was 1. Okay? And yes, the answer is still 3. Okay? I feel like this is a great stopping point. We're going to come back here and we're going to talk about a couple other logs of properties of logs, which would be like a continuation of 4.3. And then we will really get into graphing logs and how they actually all connect as the big picture kind of a thing. All right, guys, I appreciate your time. I know this one was a little longer than normal. Once again, you got to push through. If you're going to go somewhere you've never been, you're going to have to do some things you never did. All right, this is Rush Mahaber signing off. I will see you on the next video. Bye-bye.